Okay, let us see how we go about this one. It's also an easy equation, so it's just a proof. Let us see what we go with. 2 points A and B are x meters apart. A particle starts from rest at P and moves directly to Q with an acceleration of A meters per second squared until it acquires the speed V. It maintains that speed for 40 seconds and brought rest at Q and the iteration of A meters per second. Prove that that is true. So we start with the sketch. So we have 2 points P and then another point Q. So what they are telling us that it started from rest. A particle starts from rest at P. So at rest it means that it starts at 0. So it starts at 0. It goes like this until it requires a certain velocity. So the velocity they are telling us that it acquires a certain velocity, but this velocity, they are telling us that it acquires this velocity V. So this velocity is acquired in here. It acquires a velocity V. So it accelerates from rest and it acquires velocity V. We are assuming this is our velocity V. Then they are telling us that related to Q with an acceleration of this. So the acceleration here is A meters per second squared. It acquires speed V. It maintains that speed for T seconds. So from here it maintains this speed. So it means that there is not any acceleration. So it maintains the speed for T seconds. So meaning maybe we'll reach there, we shall get our T seconds. So 40 seconds. So it's now moving 40 seconds. People confuse accelerating and moving. Accelerating is the rate of change in velocity. So if the speed is not changing, the car is not accelerating, but it's not moving. So, but it's not accelerating. Anyway, so they are telling us that it did this. So from here, for T, they're telling us it did this for T seconds. Until when it was brought to rest. And then they're telling us that 40 seconds and then brought rest at Q. So after the seconds, it was brought rest at Q seconds, at Q, using a retardation of this. Retardation means the acceleration was negative. In simple terms, it was reducing its speed. Anyway, from there, what you see, we don't have this time. So let me call this time from here up to here, T1. And then we call this one from here up to here, T2. So now, we start they were telling us that prove that T is equal to that. Now, the whole of this distance, we say the distance from here up to here is x. They're telling us that it's x. What's going to happen? How do you get that distance? You know that distance, we say the distance is given by the area under this velocity time graph. So, it's the area of the trapezium. So what do we have? You see, now to get the area of the trapezium, so our distance, this distance will be equal to half h into a plus b. The longest side, then this shortest side, this short side here, and then the height from here to here. But our height is b. That's why we now prove there is a b. So now, how do I get this? That in my, I need to get this longest side. Good enough, A is long from here up to here. I know the time from here up to here. But I don't know the time because here I have T1 and I have T2. So I start with getting this. So from there, I'm going to say now I'm going now to use this triangle here. And now my velocity is given by U plus AT. Now what's the initial velocity? So the initial velocity, so here, let me call this one B. Maybe this one C. So here between P and B, you know that our initial velocity there is 0, and then our final velocity is going to be the same velocity there, which is V. Then after that, what else? I need my time. My time is here. The time from here up to here is T1. So now, I need to get what this is there. So now using my V equaling to u plus at. My v is this v equaling to 0 plus the acceleration which is a, then times time which is t1. So it's that now my v over a will be equaling to t1. So now I know what this is. Okay, so this is between P and Q. Then when I say between P and B, so between C and Q, what do we have? Now it's that our initial now here, our U, now the initial velocity is going to be now this. So our U is going to be B, and then our final velocity V, the final velocity. V final is going to be 0, the final velocity, don't confuse that. When we are starting from here, this one is acting as our initial velocity. Then this one is acting as our final velocity. But because it's probably being brought rest, the final velocity is going to be 0. So our t, the time we need there, is 2t. So using our v equaling to u plus at, our final velocity is 0 equaling to our initial, which is v, then plus a. Now note that this acceleration now is going to be negative because it's retarding. So our acceleration here is negative a. So negative a, the time is 2t. And this side from here, my v over a will be equaling to t squared. So meaning that now, if I need this, my height is going to be b. So my distance, which is given by a half h into a plus b, is that my h is equaling to my v. The height from here up here is equal to b, comma. What about my a? My a is going to be the a, this distance here. It's going to be equaling to, from here up here, they told us that it's t. What about my b? My b now I add. I'll add t1 plus t, then plus t2 to get this plus this plus this. So t2 is that my t1 is going to be v over a, then plus t, then plus b over a, my t2. So when I add these two, I get 2b over a, then plus t. So this will be my b. So now our distance, but remember, but that's the whole of this distance is going to be x. So is equaling to x. The whole of this distance, these two were x meters apart. This is not a distance. No, this is the velocity time. But don't have the distance. The only way you get the distance is by getting the areas of these things. But good enough, this is the trapezium, so we get the area of it. This is a velocity time graph. This is not the distance from here up to here. No, this is the time. And now to get the distance, we get the area of the whole of this. Because this is a velocity time graph. That's where people are confused. This is not the distance, please. So the distance between this and this is the distance over here. So it's x, which is equaling to a half into h, ha plus b, which will be a half, our h is b, into now our a, we have seen our a is t, then our b is 2b over a plus t. So I think we can add. So our x will be a half b, into this will give us 2t plus 2b over a. Multiply through by that 2. So if you multiply through by 2, our x, this 2, I can multiply through by a half, or I can of course multiply this 2. It's up to you, any will work. So there you have 2x equaling to v into 2t plus 2v over a. Divide this up in our formula, we have x over v. So divide this v side, so we have 2x over v equaling to 2t plus 2v over a. So do by 2, so that this 2 will cancel, this 2 will cancel, and this 2 will cancel. It will be x over v equaling to t plus v over a. Take this beside, we have x over v minus v over a equaling to our t. So the proof is there, which we can just rearrange. Our v will be x over v minus v over a, and the proof is done there. So that's the numbers. I wish you will. Don't confuse this thing. This is, whenever you have a velocity time graph, this is, from here, if they tell you the distance between this, is the area of the velocity time graph. Get that in mind. So that's it. Then you're going to see when we have the gravitational force in there, when we now, the motion is up, when it's going to be acted on by some gravitational force. See you there. But please don't forget to subscribe to the channel.